everyone, it's Sam from Developing Mathematical Thinking. Today we're going to look at some models and methods for dividing whole numbers. We're not going to be looking at long division, the standard algorithm today. We're going to be looking at some other methods that students learn before they learn the standard algorithm for division. If you're curious about the types of problems, story problems that you might give students, we have a video on the different problem types for division. You may want to watch that before we take a look at these methods. So what we're going to build today is we're going to use a ratio table, a method called partial quotients, and then we're going to build a visual model called the area model. Now, just a quick tip on the area model. When you actually start learning it first, you probably want to use graph paper, grid paper, to outline the area. I'm just going to be drawing it here on the board, but that is a really important teaching technique. So if you've never built an area model before, you might want to use grid paper first. Okay, so let's take a look at 492 divided by 4. The problem type we're going to try to force ourselves to think about right now is more of a measurement idea of how many 4s compose 492. So the reason why we're going to methods that we really focus on that idea. It's more of a measurement conception. It's basically answering how many 4s compose 492. So I'm going to do the area model, partial quotients, ratio table all together, and I want to show you how important they are to kind of make connections between what's actually happening. First, let's start with partial quotients. It looks sort of like we're going to do the standard algorithm for division, the long division method. You might notice that it looks just a little different because we have this long extended part here. That leads a lot of people to have names like, to call partial quotients things like the Big 7, the Magic 7, Hangman division, because it looks like the Hangman spelling game. We really suggest just saying partial quotients. That's because there are actually partial methods for addition, subtraction, multiplication, and here division. And by referring to it, so there's partial sums, partial differences, partial products. And then by referring to this as partial quotients, it sort of classifies it as the methods in which we find either the difference, the sum, the product, or the quotient in parts. It's a consistent theme for students as they learn these different methods. Then I'm going to start, next to the partial quotients, I'm going to start a ratio table. And the only information I'm going to put in it right now is just one copy or iteration of 4 gives me that product of 4. So I'm basically going to be multiplying by 4s as we go across, and you'll see how we kind of move within the table to help us actually with the partial quotients. So I'm just listing right now that 1 times 4 is 4, and that's just to get us started. Then I'm also going to start an area model, and again, this is probably best done initially on graph paper, just so the students' drawings are proportional and they really get a sense of what's happening. But I'm going to start the area model with just a length here, just this segment of 4. It's a measurement of 4. Now, what we're actually going to do is we're going to build this area model, this rectangle, to compose an area of 492. Now, if you've ever worked with multiplication, you know that you're typically presented with the area up front, but you don't know the actual total area, but you do know both all the side dimensions. Well, with division, sometimes you'll hear people call it like a reverse area model because you actually are going to build it. You're going to compose it in parts. And I always like to use the analogy of a paint roller, like if you're painting a wall or side of a house, that you have this measurement of 4, and you're going to sweep it out until you get to the area of 492. So we know this side of that rectangular area is 4. What we don't know is what the other measurement is going to be to get to 492. Okay, so let's go back to our partial quotients. First thing we're going to do is actually try to focus on place value, because that will set kids up to learn the long division standard algorithm later. So I'm just going to focus on the hundreds for right now, and I'm going to ask myself, how many times will 4 go into 400, or what times 4 is close to or exactly 400? Turns out that it's 100, so I'm going to actually list that in 2 places at the same time. I'm going to say 100 times 4 is 400. I'm going to list that on the outside of the partial quotients. And I'm going to then show that I've used 400, so I'll subtract that. I'm left with 92. And then going back to that analogy of sort of sweeping out to compose that area, I'm going to basically take that 4 and just cover a 4 by 100 area. Now, I'm not going to be able to draw it exactly proportionally, so I'm just going to suggest the proportion by making the 100 larger than the 4. Sometimes when the numbers are really large, it's hard to draw it totally correctly, but at least trying to make it close will really help. So I'm going to say that if I swept that out 100 times, I would compose an area of 400. So you can already see where these different methods connect and how they're similar. So now I need to figure out how to deal with this 92 that's left over. That's why I really like having the table work simultaneously with the partial quotients, because I can do some work here in the table and not necessarily list it in the partial quotients. So a lot of students know that 10 times 4 is 40. So I know I can at least use 40 here because I need to deal with 92. Somehow I need to compose 92. But a really good questioning strategy, if you're focusing on place value, is start with the largest place value. If 4 times 100 is 400, let's say that was maybe a 500, just ask the follow-up question, well, what is 4 times 200? And that way you'll know that you've used the largest place value unit every time. So going back to the table, well, I know 4 times 10 will work because that would be 40. So I could list times 10 out here, take 40 away, and I could do that in steps. That's perfectly fine for kids to do when they first learn this. But to be a little more efficient, we can actually use the table to help us with this. So now I'm going to say, okay, well, 10 works. What about 20? So I can double that. That's 80. And now I could actually ask the question, what about 30? And that actually ends up being too much. So I know that the most I can use with 10s is 4 times 20. So I'm going to list that out here. And that tells me that I'm left with 12. Now in the area model, I'm going to show that I've swept that out by 20. And again, my model's not perfectly proportional, but these numbers are so wildly different, it's not that easy to draw that. But if you were doing it on graph paper, that would help alleviate that issue. So one last thing on the table, a lot of people, when they first learn to use ratio tables, are a little uncomfortable that the numbers are actually now going back down. So I jumped from 100 times 4 to 10 times 4. It's actually perfectly fine. The ratio table, the basic rule here is just that the ratio of 1 to 4, that original proportion, that has to stay consistent all the way across. So every single one of these will have that scale factor of 4 as we move across. And I could actually go to, my next one could be half and 2, as long as that proportion stays consistent. Okay, so we're getting close to being done. Let's go back to our partial quotient. So I've got 12 left. I could take out 1 4 at a time until I get to 12, but I also can list that I know that 3 times 4 is 12. So now I'm going to take out 3 times 4. That leaves me with nothing left. I'm going to then also list that on the area model. And again, the proportion's not totally accurate, but just trying to get a sense of it. And then what I do to actually find the final quotient here is I found it in parts over here. So I'm going to show how many 4s in all it took to compose 492. And it turns out that it's 123. That's this measurement right here. That's how much we had to iterate that 4 out to get to 492. And then it's always really helpful to then list that information back in your table. And that leads us to the quotient in a model and 2 different related methods. One important thing to talk about with the ratio table that is sort of related to what I was talking about earlier, how sometimes people just are a little unsure of how you can jump from 100 back to 10. It's kind of just human nature to want things, if we're increasing, to just stay increasing. Another piece that the partial quotients and area model really help explain is where this 123 came from. So you have the 100 here, you have the 20, and then you have the 3. And so just like what we did in partial quotients, you're composing them all back together to get the quotient of 123. And notice in this case, the 10 was just listed as information, just saying, hey, could we use 10? Well, now what about 20? And if 20 was too small, we could have jumped to 30. So we're not actually using that 10. We're recomposing that quotient out of the different parts that end up matching the visual model and the partial quotients.